Well, welcome to the section 3.7 pre-class video assignment. For this section, we're talking about something called convolution. So before we introduce the concept of convolution, we're going to look at some of the integrals that we'd run into just for practice, sort of for prerequisite practice. So basically, let's see here. Basically, we will see this if you look at two functions, one of them f of t, the other one g of t. A convolution of f and g is defined as this integral. Basically, it is also possible to define it this way, as this other way around. So basically, f of z, g of t minus z, dz. Or you can interchange the role of f and g and do f of t minus z, g of z, dz. But in either case, it is dz, and it is integrated from 0 to t. It turns out, and we will look at this in the notes, it turns out that these two integrals will actually end up with the same result. So either way around is a convolution integral. So we can kind of think of a convolution as a special type of product. It's a way of, again, it's sort of a product of f and g. It does involve, obviously, an integration here as well. So, but you can think of it as a special type of product. It will have certain properties that we are interested in terms of DEs and Laplace transforms. So that's really where we're headed with this. But initially, let's just talk about the nature of these integrals. So the first thing to realize here is the integral is dz. Z is basically a dummy variable here. The functions f and t are functions of t, the functions f of t and g of t are both functions of t, but this integral is an integral with respect to a dummy variable z. So z did not appear in f or g, it is just a dummy variable. So again, just think about what this says. If we do this integral dz, then we are integrating with respect to z. T is treated as a constant in this integral. But once we are done integrating with respect to z, we are then substituting in effectively a z equals 0 and a z equals t into our result. Therefore, the end product here will not have any z's left in it. It will end up having t's in it. So again, this is a special kind of product. We multiply f of t and g of t together, and we get a result that turns out to be a function of t. All right, so we're going to practice working with this. And again, the key idea here is just to note that when you integrate with respect to z, treating t as a constant in these cases. So the first integral you're going to see is one where effectively the functions f of t is a t, and g of t is equal to e to the bt. And again, your question will have a randomized value for a and for b. So that's your first example. So notice when you set this up as an integral, like when you see the question, it's going to be set up like a convolution integral, like one of these, and you will basically be integrating with respect to z. So in one case, I think in the first example, you will do f of t minus z. So you will have a t minus z here and a exponential to the z here, and you will need to integrate an expression like this. So the hint is you will want to distribute the exponential one over the two terms in the other one, and then you will have one integral that is pretty straightforward and another integral that is a by parts integral to perform. So give that one a go now. The second example here is also involving f and g as written here, but this time the roles will be reversed. So you'll basically be doing the other option. So I think you'll be doing, I think you do this one. You just did this one. The second one, excuse me, this was the one you did first. This is what the second one looks like. Again, so be able to carry that through as well. The hint for the second one, where we're putting t minus z in for t, is to use exponent rules to rewrite this exponent into an exponent with t and an exponent with z separately. So that would be the hint for this second one. So give that a go. All right, so just a couple more to try out. The next one is where f and g are both exponential, simple exponential functions. So give that one a go. And the last one is an example where you have, I believe f is a function like a of t, but g is cosine. So again, the hints for the first two are also valid here for these last two. So give this last one a go. All right, so that was some prerequisite skills we will need for this section. Let's talk about, I'll introduce the topic here. So convolution. The issue here we are interested in fixing is the situation here where it turns out that the Laplace transform of a product of functions is not the product of the transforms. So more specifically written here, the Laplace transform of little f of t times little g of t is not big F of s, g of s. This would have been helpful if this were true, but it is not true. It turns out in order to get a, well, the first little thing here is just to try and work this through. The first here is really a counter example that showing that these things are not equal. So for example, the Laplace inverse, this could be the Laplace inverse of a product of big F and big G. If you do this, you'll find that this is not just e to the minus t, e to the minus 2t. It is not just the product. If you, in fact, as I wrote over here, and you can check this out here, this is what you actually get. So this is not equal to this. So this does not work. So again, this is just an example. Again, it would be handy to have an idea of what the Laplace inverse is of big F times big G. For example, if we knew an answer to this, it might give us an alternative to doing PFD. If I knew what to do here instead of PFD, it could give us an alternative. And there are other applications as well. And it turns out then this convolution that we've been talking about is basically the answer to this question. The convolution of f and g of t. This is the notation for it. So this asterisk, and definitely in this section, this asterisk means convolution, not just a product. And again, it is defined by this integral as we had previously mentioned here. So this is the convolution of f and g. Again, so we mentioned a couple of these things. A convolution is a special kind of product. The result of convoluting two functions of t is another function of t. Again, the z ends up being a dummy variable. Once you're done integrating with respect to z, you end up plugging in t for z, so you end up with a function of t. So again, we end up convoluting f of t and g of t and getting a function of t as well. Due to the endpoints of the integration going from 0 to t, a convolution is only defined on the interval from 0 to plus infinity. So that's this is sort of a domain issue here. First little thing here that is a handy little bit of information is that convolutions are commutative. F convoluted with G is the same thing as G convoluted with F. So here's a little proof. It's actually fairly easy. If you start with F convoluted with G, it suggests this integral. So making a clever substitution, if we let v be equal to t minus z, so this is sort of the obvious idea to try and rearrange it to be the other integral, would be to make z be equal to t minus z. So, but notice if v is t minus z, dv is minus dz. Also, we can solve this for z and get z is t minus v. We can also understand the endpoints of integration. Again, technically, when we write this integral here, just remember that we're really saying z is from 0 to t. So if z is 0, when z is 0, in our relationship here, when z is 0, v is t. When z is t, v is 0. So completing these substitutions in here, we get the following. We put in our t minus v for z. We put in v is for t minus z. We have a minus dv. This is related here. And then we have these endpoints that switched. So the clever bit here is, well, the t ended up down in the lower endpoint of integration instead of the upper endpoint of integration. But if we want to switch them, which we do, we can just change the sign. So switching them gets rid of the minus sign, and we end up with this guy right here. And effectively, this is nothing more than the definition of convolution, where we have G convoluted with F. So we started with F convoluted with G, and we now have here that this is equal to G convoluted with F. So you can treat them or set up this integral either way. You can put the t minus z into the G and just the f of z is the other one, or you can put the t minus z into the f and just leave the other one as g of z. All right, so this one here, you have already practiced an example similar to this, but again, here is some work to show the convolution of t and e to the 2t. What would this look like? So I am setting up the convolution of f convoluted with g. So f is just t, so that is just this. This is e to the 2 t minus z dz integral from 0 to t. So in order to carry this integral out, the idea is I want to apply exponent properties here. This is e to the 2t minus 2z. So this is e to the 2t times e to the minus 2z. So this integral is with respect to z. Therefore, e to the 2t is a constant with respect to this integral. So this can be moved outside. So e to the t outside, and then I just have an integral of z that I can work on. So this is actually a fairly straightforward by parts. So I wrote out the by parts here. You should get an integral that looks like this. And again, completing the integral, we are plugging in t for z, and we end up with something like this. Now, last thing to do, I can redistribute e to the 2t to clean this up a bit. E to the 2t times e to the minus 2t is 1. So that cleans up a little bit. And this is what we get as our final answer. It might be interesting to check out the commutivity here. That is, you could try and set this one up the other way around. Try doing it as a g convoluted with f of t, and see if you don't indeed get the very same result here of this guy right here. You should get the very same result either way. Let's just look at one more here. This one's perhaps a little trickier, but the convolution of sine omega t and cosine omega t. What is the convolution here? So yes, we can write down by definition what the convolution is, and then the question becomes, how do we integrate something like this? The answer is perhaps not obvious. It's something that we run into occasionally, but infrequently enough that it's hard to remember. But the idea is there is a trig identity for simplifying this sort of thing. So we're going to use this trig identity. If you apply this trig identity, we can then break this down into these two guys right here. So these can be integrated directly, right? So this was a problem because we had a product here. This is easier because this is not a product. This is a sine function and another sine function, dz. So this first one is not a problem at all. It has no z in it. Treat this like a constant, yes. The second one is a little awkward looking, but also not difficult. It is just make a little U sub out of it if you want to, if you're having trouble thinking it through, but we can make a little U sub out of it and we get something like this. So at that point, again, we are finishing it off by making our substitutions. Z equals T first, then Z equals 0 second. Notice that this guy here and this guy here are actually equal. Omega t minus 2 omega t is cosine of minus omega t, and cosine is an even function. So cosine of minus omega t is cosine of omega t. So this and this cancel, and we get our answer. So that's all we're going to cover here. We will look at a little bit more about what convolution does for us in terms of Laplace transforms and some DEs and some other applications in class together. Thank you.